and go from current slide. Oh no, that's not the right. I should have been paying attention. That's not the section we're on now. So I need to go back and find out which one we are on. Is it 4 or 6? Let me see about 6. I don't think that's right either. See, I was just killing time and I should have been doing this. Nope, that's what we're going to do next. So let's do 4. I think that's it. So we'll do slideshow. Sorry, I started it too soon. That's it. Okay. Now, my sad story. I think I told you this before, didn't I? Wait. Yeah, I told you that last Friday I got 0 done as far as the syllabus and that kind of stuff because it was just crazy. I'm hoping this afternoon to be able to make progress on getting your Blackboard set up and all that kind of stuff. I've got 7 classes right now. One of them is completely set up. Most of the rest of them are ready to go. I've just got a few little things to check on and make sure all the data's right in the syllabi and things like this. I've upgraded everything. So hopefully I'll get to do at least one more this afternoon. No guarantee. I've got to get 2 purchase orders done this afternoon because they close out purchase orders tomorrow, Friday. So I've got to get those done. My printer is out. The ink cartridge is almost gone, and another instructor's printer is almost gone. So I've got to get those 2 done today, and then I hope to be able to get to work on getting syllabi done. If not, it'll be Friday because I have no office hours on Thursday to speak of, and hopefully Friday won't be as crazy as last Friday, but you never can tell. So anyway, now, yeah, it's 5.5 in the new book, 5.4 in the old book. Which book have you got? Have you got this one? Okay, yeah. 5.5 in this one. This is leading into fundamental theorem of calculus. And this is just a little bit of review. This is an area function. That's why we call it a of x. And what that is the integral from little a to x. I sort of wish they did do this. This a has nothing to do with that a. This is the beginning point here that you're doing the area under the curve. This is the area under the curve. Okay? Of f of t dt, whatever function that is, we'll assume it's a non-negative function. All the values between a and x are positive. But even if not, it's a signed area. So if some are negative, then they go negative. Okay? So it's the signed area between a and x. Whatever x is, that's the area, right? That's what an integral tells you, the area under a curve. Area under the curve, f of t, as t goes from a to x. That's the area under the curve, right? That's what integrals are telling us. All right. Now, there's the figure that illustrates that, okay? There's your f of t, the pink line there. They show it all positive. It could be negative because we're talking about signed area, but this is positive. So going from a to x, that's the area, and that's a function of x. You extend x out here, it's a bigger area. Bring x in here, it's a smaller area. So this is a function of x. Given a point, but that's the a is a function of x. Does that make sense? All right. Now, this is the first example we're not going to do, but let's just mentally think through it anyway. Here is the curve y is equal to t squared. Okay, you can say f of t is equal to t squared. From 3 to x, where x is some value out here somewhere. Now, if you integrated this function, t squared dt, what's the antiderivative of this? T cubed over 3, exactly. Evaluate that from 3 to x. Well, that would be, when you evaluate the x part, that would give you 1/3 x cubed. That's that part. Minus, and when you put that in, the 3 in there, that would be 1/3 of 3 cubed. 3 cubed is 27. 1/3, third of 27 is 9, so minus 9. So that's the area under here, a to x. Now, of course, this makes sense for any x is greater than 3. If x is equal to 3, that's 0. Okay, no area. If it's less than 3, then you've got a negative area because you're going in the wrong direction. This is for any area x greater than 3. This is the value. So if x is 7, plug into 7. If x is 4, plug into 4. And that's your area as a function of how far from 3, what value of x you got there. Okay? Make sense? All right. Now, here is the fundamental theorem of calculus part 2. Remember what part 1 was? Oh, it was so long ago. Part 1 was basically how you evaluate a definite integral. Take the antiderivative of whatever is in the integrand, and then fill in those things, just like we did here, that we use that. Okay? Now, assume the f of x is continuous on some open interval I. That's a good thing to have. In order to integrate, you need really it to be continuous. Okay? Over some interval I, and let a always be in that I. Now, what they didn't say, oh yeah, f of x, so that means all the x's are in that same interval I too. Okay. Now, that integral is an antiderivative of f of x. Okay? That is, if you take the derivative of this, you get f of x. Okay? Or, another way of saying that, if you take the derivative of this, you get that. Okay? Now, it almost seems like you're running around in circles, right? But you're really not. Remember back in maybe even preschool or first grammar school or something, you learned how to add, and then once you just about finally got that down, then they turned around and had you start doing subtraction. What was subtraction? Undoing addition, right? You didn't call it that then, but that was an inverse operation of addition. You undid addition. Well, then you multiplied, right? You thought, got all my tables done, let's do multiplication. So you had all those to do. But then once you got that done, when you divided, you undid multiplication, right? That was an inverse operation. Inverse, yeah. Okay? Well, then later, and then you did squaring, and you took square roots. Powers, and you took the roots, you know? You did exponents, and you took logarithms. Those were inverse functions of each other. We did that in pre-calculus. Inverse functions. There's a whole process. Well, this is sort of the same thing. If you'll notice here, if you take the derivative of a function in an interval, you get the function out at that value, the x value, the upper value there. Okay? That is saying that if you integrate a function and then differentiate the function, you get the function. Differentiate the integral, you get the function. And you can also do it the other way. If you integrate the derivative, you get what you're taking the derivative of I. So these two operations are inverse operations of each other. Not inverse functions, these are whole operations. And that's what we call antiderivative. An integral undoes a derivative, and a derivative undoes an integral. That's the second fundamental theorem of calculus, part 2. That integration undoes differentiation. Differentiation undoes integration. Okay? I don't know that this is anything worthwhile to look at. It's part of the proof here. And if you're doing the area under a curve, part of that is doing your area here times dx. The area was the area from a to x, or a to x plus h, minus the area of a to x, and that gives you this part here. Well, that looks like the top part of the derivative, doesn't it? A, f of x plus h minus f of x over h. Sure enough, that's what we did when we were taking the derivative, and here we are doing integration. One undoes the other. Okay? So, that's part of the proof. We're not going to do the proof. This is almost the same picture. I'm not sure why they did it twice. It's just saying the shaded sliver lies between that rectangle and this rectangle. The area under here is that. So basically, you're going back to a Riemann sum type idea. Why you go back to that, but it's perfectly fine. Yeah, sorry. If what we said before, they're the areas, then that this thing is also the area, difference in areas between this one and that one. And that does come out to be what your integral is. So yeah, that completes the other side of it. So basically, and again, without doing the formal proof, this sort of seems disjointed. So the limit of remember, f of x times h, that width here, gave us what all right. The difference between f of x plus h and f of x times delta times h, which is your width there, that gives you the area of that sliver. The area of the sliver is also a of x plus h minus a of x. So if you multiply this one by the delta h there, then you get this one, okay? That's basically where they're going with this. And what that basically tells you is that the integrand, that was what's inside the integral, is equal to the derivative of the answer for that area. So this is the other side of the second, the fundamental theorem of calculus, part 2. Well, they don't put the conclusion down. And again, we're just going in a slideshow, so this is kind of disjointed. But you have to, this seems like it's just jerked out of the air somewhere. And it's supposed to help you see something, but for the life of me, I don't see, I see what they're saying. This is a function, strange function, but it's a function. You can evaluate it, and as you're going from here to there, the areas, notice you start here, the area is 0 when you start here, and then you increase this area a little bit. This is your area here, and then you're not increasing very much because it's getting smaller. Right now, you're not increasing at all, but now you're increasing again, and you're stopping here, this is where that would be. Now, so this was gradually increasing until you get here, and now you have to start subtracting the area out. So now your total area decreases a little bit, then it starts increasing. It decreases all the time you're in here, and then it starts increasing once you get a positive area again, and then it decreases a little more while you're in here, and then it starts increasing again while you're there, and it keeps on going. Yay, okay, I see that. What's the point here? This line here, y is equal to f of x, is the area under this curve, the integral from negative pi to x, wherever that x is, of this function here. Okay? That's fine. Let me give you a little hint. We can't analytically do this integral at all. Period. That's not integrable. Okay? We have no technique that will work to give us that. And yet, we can find out by a method like this what that integral really is. Okay? If you do this kind of thing. This function here, if you can come up with it, that function is the area of the vector. Why are they doing that now? I'm not really sure. But that is definitely true, but I really don't see the point of it at this point. Okay? This is part of example 4, and again, we're just sort of doing this real quickly. The fundamental theorem of calculus part 2 does not apply okay. Again, this is part of example 4, and since we're not doing example 4, we're not going to do it, but here's what they're trying to say here. If this is your curve, y is equal to f of x, and you're talking about the incremental area under the curve, at x1, when the function is a smaller value, the incremental area is less than it is the same delta A at a larger value, okay, when that's an increasing function. Sure, okay. Again, I'm not sure why they chose to throw that in here, but it's perfectly true. And the last slide in this section, or at least I think it is this one. And I'm not sure it's, without doing the whole section, it's going to make a lot of sense to you, but let's see what it says here. Oh, it's the same thing I was showing before. If you have the blue line is y is equal to f of x, that's what you're integrating. Well, that's going to be a positive area here, and then you're going to start losing area. So as long as between here and there, it's a positive area, so the area is increasing. As you let your x increase here, your area is increasing. Then when you let your x increase here, you start losing area, subtracting area from it, so this is decreasing here, or that is this. But when you get here, it starts increasing again, and it keeps on increasing, at least to the end here. Okay?
That looks just like so we're doing count one.
Yes, exactly. That is what you have if you're doing a derivative of this, that was your take. In Cal 1, and you started with this function, took derivatives of it, this is what you got. You're absolutely right. This is the graph. So you see, that's what I'm saying. Integration undoes differentiation, differentiation undoes integration. That's what the fundamental theorem of calculus part 2 tells you. Okay. Thank goodness that's it. Okay, no, I'd say we're through with that. All right. Now we start in what I feel like the real beginning of Cal 2 is. Okay? I'm clicking and it's not exiting. Let me do that, see if it'll exit. There we go. All right, now we're moving to 5.6. On this it says 5.5. Yes, this is where we begin. Now from this point on, we're going to do all the examples. This is what you're going to be tested on, beginning of what we do. That was all the stuff we didn't get to cover in Cal 1. Okay. All right. What they say here, so far we have focused on area interpretation of an integral. In this section, we use the integral to compute net change. No, I'm sorry. This is not where I was going to start. Sorry about that. It's 5.6 in the old 5.7 here. I usually skip this one anyway, so I'm not even going to go through the slide set here. It's pretty short, but it basically is kind of using fundamental theorem of calculus part 2. Since I usually skip that anyway, let's get out of that. Sorry about that. And that's right. It's 5.6 in the old, 5.7 in the new. So I got them backwards. This is where we're starting, not that, this. What's that? Substitution method. To me, this is a technique of integration. Okay? All right. Now, finally. Integration, or think of it as anti-differentiation, okay? Generally more difficult than differentiation. Derivatives are certain rules, you take them, you do them, okay? There's no surefire methods. You keep trying things until you get something that works, okay? Many antiderivatives cannot be expressed in terms of the elemental functions. However, there are a few important techniques, and this is the first of these techniques. It's called the substitution method. Now, if you remember, when you're doing derivatives, once you got your feet really comfortable in doing derivatives, then they introduced something called the chain rule. Remember, that was fun, wasn't it? Yes, I can tell. Okay? The chain rule is if you had a composite function. You had an outer function and an inner function. The chain rule allowed you to take derivative of those. Okay? Now, so maybe the best place to start, and that's actually where they did start, so maybe I should back off here. Okay? All right. Start with the chain rule. Okay? What if we had this as a function? So it's almost like the same thing we had before in that last set we were doing, just showing the slideshow. What if you have a function, f of x is equal to sine of x squared? Okay? You can get you a package and graph that. You can do various things with it. But what I want you to do is take a derivative of it. So you want to do f prime. And you remember how to do that. Good old chain rule. How was that? Remember how it worked? Okay, no. You're right first. Derivative of the outer function, which is cosine of x squared. But then you add times the derivative of the inner function. Okay, which was 2x. There's the derivative f prime. That's the chain rule. Okay? Take the derivative of the outer function, then multiply it times the derivative of the inner function. And you can do that for as many nested functions as you want to. You just have to keep up with them. Okay? Now, what that tells us from the fundamental theorem of calculus, if you were taking the integral of 2x cosine x squared dx, right? If you're doing the derivative, the integral of that, you should wind up with what you started with, sine of x squared. Okay, you should wind up with that because integration undoes differentiation, right? Differentiation undoes integration. Except, there's always an exception, isn't there? You can only come within a constant of it. So you always have to do a plus c. Okay? Because when you integrate an indefinite integral, that could be any of functions. And it could be some multiple, not multiple, some constant vertical shift of that function. Okay? Now, they do a couple more, and they kind of skip over some things here, but let me do them because they're doing them this way. What if you're trying to integrate this 1 plus 3x squared times the cosine of x plus x cubed? Okay, dx. Okay. Well, that almost, first glance, looks like a product rule problem. You think, oh my goodness, how do I do that in antiderivative? But it's not, because we're going to look first and say, this is a composite function. What is the derivative of its innermost part? What is it? Derivative of the innermost part. Derivative of x is 1 plus 3x squared. Well, guess what? That's what you got out here. So this lets you know, hey, that is just the antiderivative of the cosine of, the antiderivative of the cosine of this. What's the antiderivative of the cosine? Okay, that's okay. Derivative of sine is positive cosine. So therefore the antiderivative of cosine is positive sine. Derivative of cosine is negative sine, meaning the antiderivative of sine is going to be negative cosine. The signs flip because you're going in the opposite direction, remember? Okay. So this will be sine of this, sine of x plus x cubed. And if you weren't sure that's the answer, take a derivative of it. If you get that, yeah, you got it right. Because an integration is an antiderivative. Undoing a derivative and taking a derivative should give you the inside of a function. Except, as I said, that's going to be sine of x plus x cubed, but then you also have to do the plus c. Because it's an indefinite integral, you may be off by a constant. Okay. Now, what that leads to then, if the thing you're taking a derivative of, and there's a part of me that almost wishes they wouldn't use the capital, but I think I know why they do. It makes you think they're related, and they are. So if d by dx of f of u of x, okay? There's your good old composite function. Whatever f is, but then you're operating on some other function of x, okay? That derivative by the chain rule would be what?
What's the neighbor next to x?
Say again?
What variable is that next to x?
I said that here.
Oh, it's f to what?
F of u of x. Is that what you're asking?
Yeah.
Yeah, okay. I'm hard of hearing if you hadn't picked that up, okay? So what's the derivative of alpha of u of x? f prime of u of x and it doesn't matter where you write it. What's the second part? Yes, u prime times u prime of x. And you can either write it in front or write it at the end. It doesn't matter. Okay? If that's taking a derivative, then if you integrate this, you're going to get this plus c. Okay? So in other words, if you have an expression, pull this off. This part down here. Boom, I blew it up. Okay. If capital F prime is the same as little f, okay? In other words, capital F is the antiderivative of little f. If capital F prime is little f, then the antiderivative of little f is capital F. Okay? The derivative of capital F to little f, and the antiderivative of little f is capital F. So if you're integrating f of u of x times u prime of x, then, I'm sorry, I said it backwards. Yeah. Then the antiderivative of f is capital F of u of x plus c. Okay. Now, this is a little heavy on blah, 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 isn't it? Let's get the technique down for how we really do this. Okay? First, just a little reminder here. That is differential form, okay, of, okay, you're familiar with that? This is the differential, hit the wrong key, okay? This is differential form of this derivative. du dx is equal to u prime of x, right? You buy that? Those are just different ways of expressing. That's Leibniz notation, that's the prime notation. They mean the same thing, right? Okay. Well, the pure mathematician would grunt if I said this. Move the dx over here, and you have du is equal to u prime of x dx. That's written in differential form. The advantage of differential form, these are easier to integrate. Okay? So this is just a reminder. This is a truism. That's an identity. It's always true. Just rewritten a notation issue. Okay? So, let's follow that up with this. What if u is equal to x squared? Okay? Simple thing. Then you tell me what du is, written in differential notation. Two x dx. Perfect. See? If u is this, then u prime would be 2x. So du would be u 2x dx, right? It's just another way of doing a derivative, only you're writing in differential form. You okay with that? Does it make sense? Okay, that's key. That is a key for doing the substitution method. Okay, let's do another one. Let's let u equal cosine of x cubed. Then, what is du?
You have to apply the chain rule to this?
Say it again?
Do you have to apply the chain rule to this?
Absolutely.
So I guess it will be 3x squared
Okay, there's going to be a 3x squared in it, for sure.
times sine x
Okay, except what's the derivative of cosine? Negative sine x cubed. One more thing. Dx. Got it. Everybody follow? Okay. Now, I don't know, it sounds like you're having a little trouble with the signs of derivatives and sines and cosines, the SIGN of, okay. Here's one way that I remind myself what they are. Think of the graph of a sine, right? Sine starts at 0 and does this, right? And it continues like that, right? What's the derivative of that? The slope of the tangent line, right? What does that look like the slope of that tangent line is? 1. That looks like the slope of 1, doesn't it? Even in my ugly drawing, it sort of looks like it's a slope of 1. Well, that's what cosine is. Cosine starts at 1 and does this number, right? Okay? Now, derivative of cosine then should be 0, and sure enough, that's what sine is. But if you'll notice here, the derivative here starts going downhill, so it's negative. So the derivative of cosine is minus sine. It starts at 0, but then it goes negative. But derivative of sine starts at 1 and is positive for a while until it goes here. So you see, derivative of sine is cosine, but derivative of cosine is minus sine. If you remember how the graphs look, that should help you keep straight on that. Okay? Does that help? Probably not. The stairs were just blank at the end. In fact, worse, I think. They got confused blank at the end. Okay. So if that doesn't help, don't worry with it. Okay. Sorry. Now, here is what we do in the substitution method. Okay? If you're trying to take the derivative of some complicated looking function that looks like it has a product in it and stuff, well, take the kind of the innermost part of the outer function and let that be some other function. Okay? This will make more sense later. So, in other words, whatever is the inner part of the outer function, let that be your u of x. Okay? I'll give you a different way to say this later. And then if that u of x, if its derivative is in that original thing, then that can be your du. Well, then this becomes f of u du, and that integrates to be the antiderivative. That becomes integral f of d to u du. And if you can do that derivative, you got it made, and then back up and do this one. Okay? Now, that's a lot of blah, blah, blah. Let's actually put it to practice. Here is example 1. Okay? So let's do example 1 here. Evaluate this. Okay? The integral of 3x squared times sine of x cubed dx. Okay? Now, here's the way I approach substitution. Find the most complicated, the most involved part of the problem. That's the sine. Okay? Look at the innermost part of the sine. That's 3x cubed, or x cubed. Let that be our u. So that's where we begin. Make a substitution here. Let u equal x cubed. The innermost part of the most complicated part of the problem. Okay? Okay? Now, then, just like we did before, what's the next step? du is equal to 3x squared. Second?
Cosine?
Ah,
Negative cosine? No.
dx. Don't forget to complete your differential. Okay? Now look at this. This part right here is du. And this part right here is sine of u. So your new integral becomes the integral of sine of u du. Right? This is the u. So you got sine of u, and this part here is the du. Can we do that antiderivative? Please say yes.
Yes.
How? Okay, I agree there's a cosine there. The antiderivative of sine is negative cosine u, right? Because the derivative of cosine is minus sine. So you have to have that minus there. But then we have a plus c. Now you can wait and do the plus c later if you want to, but that's an indefinite integral. It's going to have a plus c. But you know what? The problem didn't originate with u in it. It originated with x in it. So now we have to substitute back in what u is, or u are. No, never mind, whatever. It'd be minus cosine of, and what's u? X cubed plus c. There's your answer. Okay? Minus cosine x cubed plus c. And if you're not convinced that's your answer, take a derivative of it. And when you take a derivative of this, you should get what's inside your integral. And you will exactly. Okay? Right?
Do I have to like do it the long way?
Say again?
I mean, I said, do I have to do like the way you do it?
No. As long as you do it right, I'm happy. You do it wrong, I'm not happy anymore. Okay? I have to take off points. I'm not happy if I'm taking off points. Okay?
So essentially, all you're doing is taking the antiderivative of the sign and then just rewriting what's inside the parentheses.
If the outer part is exactly the derivative of the inner part, guess what? We're going to get some that aren't. And then we have little other things to do. So you can skip steps when they're easy, and when they get a little harder, you're going to have to put them back in. So as long as you recognize that, fine to do it that way. Okay? I'm happy. I'm happy if you give me right answers. If you don't, I'm mad at you. Okay? All right. Let's try another one. Can we do it on the bottom part? Is that too crowded? Want me to clean the slate? Okay, let's do it. Let's evaluate this. The integral of x times x squared plus 9 raised to the 5th power. That's supposed to be an x, okay? One is making me write ugly. Okay. Where would you begin? Okay, yeah, let's find a u. Let u equal something. And what u I can use going to be?
Would it be x?
X.
X squared plus 9.
Ah, I like it. X squared plus 9. Do you like it too? The innermost part of the most complicated part of the problem. The most complicated part is the 5th power, the outside part. Choose the inner part of that. So let that be our u. And what's the next thing you determine? Then du is equal to what? 2x dx. Very good. But we don't have a 2x dx, do we? We have an x dx, right? Right here. This doesn't have a 2x. So what I have to do is divide both sides by 2. And now I have an x dx, right? So du over 2 is equal to x dx. So this part right here is now my du over 2, and this part right here is u to the 5th power, right? You see that? Okay. So let's take that 1/2 out front. You don't need that in the integral, do you? And you have the integral of well, I don't want the du there. You have u to the 5th power du. Do you buy that? This is u to the 5th power, and this is du over 2, so I'll pull the 1/2 out front and leave the du. You see that this is that substitution. Can you do that integration? You say yes. How do you do that? The antiderivative of u to the 5th. Say again? You're taking the derivative, aren't you? I said antiderivative. Oh!
So it would be 6,
u to the 6 over 6. Right? Both of you agree? Okay. And we can put a plus c. Let's hold off the plus c for now. Okay? Now, next thing, plug in what u is, or u are. Okay? And that will be 1/2. Let's make it 1/12, okay? Because you got a 1/2 and a 1/6. So that's what, oh, I didn't need to do that. Okay. I could have just written 1/12. Okay? And u is x squared plus 9 to the 6th power. Right? Plus c. Don't forget your plus c. See, I didn't want to write it in too soon because I was going to multiply by 1/2 that kind of stuff. Just to be sure at the end to put a plus c. Let's see how the book did. Well, it takes them a while, doesn't it? 1/12 u to the 6 plus c. Well, plugging that in, 1/12 of x squared plus 9 to the 6th power plus c. Good for them, they got it right. See how it works? Okay. Ready for another one? Sure you are. Okay. Let's do that. Did I need to leave that up any longer? Sorry, I should have asked. We all go through. Okay. Let's do this one. Evaluate this. This is getting really good looking, isn't it? X squared plus 2x dx over x cubed plus 3x squared plus 12 to the 6th power. Anyone want to do that right off the top of your head? I don't think so. I don't either. Where would you begin if you're going to try substitution? Since that's the section we're on, a good thing to try. Where do we begin? Yes, the denominator is the most complicated looking part of that problem. So let's do the innermost part of that denominator, which is that u equal x cubed plus 3x squared plus 12. What's your next step? Then what? du is equal to 3x squared plus 6x. Done. X out for dx. Okay, don't forget your dx. All right, do we have a 3x squared plus 6x dx in the original problem? No, we don't. But what could we do? To this. To make it look more like that. Yes, factor out of 3. Don't just go dividing. Factor out of 3. Or divide both sides by 3. That would be legitimate too. So then also, if you want to divide by 3, du over 3 is equal to what? X squared plus 2x dx. And that is what we have up here. So this thing up here becomes du over 3. What does the denominator become? Second? U to the 6. So this becomes, now what do we do to this 1/3? Let's take that on the outside. 1/3, the integral of this thing here then is just du, because the 1/3's on the outside, over u to the 6. Is that what you said? Now, can you do that integration? Can I make a suggestion to you? You open to suggestions? Okay. I don't like to integrate things that have things in denominators. If possible, move it to the numerator, even if it means using negative exponent. So I would change that to be 1/3 the integral of what? U to the minus 6 du. Okay? Can we integrate that? How? It's the rule for integrating a power function. All right, u to the negative what? Okay, what was the rule again? You subtract the power. Second? Negative 5. You add to it, remember? Yes, okay. You're adding with a negative number, so that becomes a negative 5. You got to do something else. Over what? Negative 5. Well, I'm going to put the minus there and put the 5 down there. You okay with that? You buy it. Okay. Now, I'm going to rewrite that. I'm going to pull the minus all the way out. I'm going to pull the 5 all the way out and make that minus 1/15. By that, u to the minus 5. Okay? But the original problem didn't have any u's in it, so why should our answer have u's in it? So what will we do? And I think I would also, since that was in fractional form, let's put this in fractional form. X cubed plus, the u is this thing, x cubed plus 3x squared plus 12 to the 5th. Okay? Plus c. That, I think, is our answer.
All that over 1.
Say again?
All that 1.
Yeah, 1 is in the numerator. All that is under 1, yeah. Okay, so I didn't write it very neatly, did I? Let's see if we can find where they did the answer. Okay, They did they left it thing to the -5. They didn't put it in the denominator, which is fine. You don't have to. But I thought since the original problem had it in the denominator, I put it there too. And this, by the way, illustrates to me why I do not, another reason I do not like these packaged, computerized homework assisted programs or whatever. If, like WebAssign or something like that. If it were that, it's looking for one answer. This answer is just as correct as that answer. There's no reason it's any worse. But if I wrote that answer down, but it was looking for that one, it would say it was wrong. Where it wasn't wrong. It was just in a different form. So that's one reason I don't really care for those packages. I spend more time saying, no, you're right. It is, they said it wrong, but it really is right, okay? And here's why it's right. But it's pretty frustrating to students, I think, to be told a correct answer is wrong. Then you think you did the problem wrong, and then you go back and change your whole way of thinking. You did everything right, you just wrote it in a different form. So I really don't care for those packages if you haven't figured that out yet, okay? Now, there is a little conceptual insight here. I don't think they're going to show it on the slide. I'm pretty sure they're not. No, they're not. Let's take that same problem we had and do this. Almost the same problem. X squared plus 2.1x dx over x cubed plus 3x squared plus 12 to the 6th power. What would you do with that? Say again? No, you hang it up. You do numerical integration because there's no way in the world, because you see, if you did the same thing, you're going to get the same thing for du here, and that is not the same as the d what you have here. There's no way you're going to get this one using substitution. In fact, there's no way to work that problem except with numerical integration, which we haven't gotten to yet. So, this will work if things are exactly the right numbers to do. If they're not, got to try something else, and I'll tell you that can only be done by numerical integration. And guess what? In real life, most of the time things aren't real pretty like that. They will be weird-looking things like this, and really the only way that we can do it is numerical integration. But in those cases where you do have that, it won't be far off from this, so this will give you a good estimate of your answer, but it won't be exactly right. Okay? So, warning. Okay, let's go to example 4. Whoops, hit the wrong key. Any questions before I delete that? Okay. Example 4. Let's do this one. This is just for one. He loves doing trig ones. Okay? The integral of sine of 7 theta plus 5 d theta.
Actually,
What's that?
I said I failed a trig once.
You did what?
I said I failed a trig.
Oh. You sure could have fooled me. No, I'm just kidding. Okay. Did you go back and pass it later? Yeah. Good. All right. What would you do on this one? Okay. Did I hear I'll let you? Is that what you said? 7 theta plus 5. Then du is equal to 7. Second? D theta. Okay, I couldn't hear the D there. Everybody agree? All right. Problem, Houston. We only have a d theta up there. So what do we do? Divide by 7. Yes. Okay. Now we have a d theta. Okay. So this becomes, the d theta is 1/7 du, so pull the 1/7 on the outside, and you have a du. There's your 1/7 du. And then what do we have on the inside? This right here is u. So what do we have? Sine u. Don't we? You just put u in for 7 theta plus 5. Right? You see it? That's the only part you substitute, is that u be this. So put u in where you have that, put that in. And where you have d theta, you put this in. So you have 1/7 sine of u du. Du over 7. Okay. Now that is an integral. Can we do anything with it? It's the antiderivative of sine u. Knew that I was going to ask that, didn't
Would it be negative cosine?
you? Got it. Negative cosine u. Okay? But our original problem didn't have u's in it. It had theta. So let's go back and put what u was. Negative 1/7 cosine of, and what's u? 7 theta plus 5. One more thing. Second?
Plus c.
Plus c. Got it. All right. Let's see how they did. Negative 1/7 cosine 7 theta plus 5 plus c. Make sense? All right, good deal. Now this next one I don't think will be all that, take that much room, but I can erase if you want me to. Just write it. Okay, let's do this one. The integral of e to the minus 9t dt. How do you think we're going to do that? Let u equal what?
E to the
Negative
negative 9t.
9t. Perfect. Then du is equal to negative 9, except it's not an x. Dt. Okay. Delirium tremens. No, that's not it. Okay. Now, we don't have a minus 9 dt, we just have a dt. So what do? Divide by negative 9, both sides. Okay. So these go out. So now your new integral becomes negative 1/9 times the integral of what? E to the u du. And I think probably we can do that one, can't we? What's the antiderivative of e to the u? E to the u. It's pretty simple, isn't it? I love e's. Okay, derivative of e to u is e to u. Antiderivative of e to u is e to u. Okay, except we didn't have a u's in the original problem, so what do we put? to the negative 9t plus c. Good deal. All right. And that's exactly what we got. Negative 1/9 e to the minus 9t plus c. All right. Oh, that was going so well. But one demanded another trig one, so we got to do another trig one. All right. So let's do it. Let's integrate tangent theta d theta. That looks simple enough, doesn't it? I see head shaking. Okay. It would be great if the tangent was a derivative of some trig function. But it's not. So, yes, very good. Let's rewrite this as the integral of sine theta over cosine theta, because that's what tangent theta is, d theta. Okay? Now what? Second? Okay. And what do we usually choose to be the u? Most complicated part. The innermost part of the most complicated. What's more complicated, the numerator or the denominator? The denominator. Let's let that be it. Let's let u, if you like u, fine, equal cosine theta, d theta. Okay? No, I'm sorry. One made me do that. I'm sorry. I didn't mean to. Okay. Equal cosine theta. What's the next step? Then du is equal to? I can't hear. Missing something. Negative sine. Okay, when you're taking the derivative of sine is cosine, derivative of cosine is negative sine. When you're integrating, the integral of sine is negative cosine, the integral of cosine is sine. They're reversed. Because they're undoing each other, right? Negative sine theta, d theta. No, that's right. That's right. Okay.
You divide on negative sine theta out?
Not negative sine theta, just the negative. Negate both sides. That's all you have to do, because you got a sine theta d theta, right? We want to keep that. We just don't want the minus sign. So you put the minus sign on the outside with the du. So this now becomes the minus the integral of what? Sine theta d theta is what? Du. It's a minus du, but I pulled the minus on the outside. And the denominator is? Which is? U. There we have it. Now can we do that integral? Antiderivative of 1 over u du. Or u to the minus 1 du. I like 1 over u in this case. Anyone remember that one? Okay, that is, okay. Are you saying the answer is 1 over u too? Yeah, it's 1 over u du. The integral of 1 over u du. It's what? ln, exactly. That's minus log u. Perfect. Now what do we need to do? Back up and undo that, and that would be minus the log of, what's u? Second? Cosine theta. Okay. Now before we do anything else, here's a rule for logarithms. Minus a log is the same as the log of the inner part to the minus 1. you can pull the coefficient up and make it the exponent. You remember that from logarithms? If not, go back and review those. I think, let me look and see. Algebra. Don't see your log rules here. Trig, I don't see the log rules here yet. See if in the back of the book. I can't ever remember, I teach from so many different books, what has what in it. Yes, yes, yes. Go to back inside cover of your text, okay? There's some heavy-duty cardstock pages there. Right after the, I think it's the index. The first one is elementary functions. We're not interested in those now. Turn back one more page from that, or one more page over from that, exponential and logarithmic functions. And here are those, well, they don't give them all, but they give enough that you can get by with. The log of well, they don't do ln, yeah, they sort of do, but not exactly. Do the log, but make it ln. Ln of x over y is the log of ln x minus ln y, okay? Or, here's one. Ln of x to the r would be r times the log of x. Well, this is doing the reverse of that. R times the log of cosine theta would be log of cosine theta raised to the minus 1. So that's what we did. That rule. Do you see that? Do you have that in your back of your text? Or you have a cheat sheet on it? Okay. Can you find that on yours?
This one, I just don't see where you're talking about.
Right here. Right here. That rule right there. If you make the r be a minus 1, you go from here to there. So this is all differentiation and integration. Doris, give you that?
It's a copy of.
Okay, yeah, well, don't go that far back. Okay. Right before this. Okay. But what's one cosine to the minus 1 is the same as 1 over cosine, right? Yeah. And what's 1 over cosine? You got it. Log of secant. Okay. Now, the only trouble is you can't take the log of negative numbers, so you have to make that absolute value of secant theta. Okay? And then you can put your plus c. Okay? What's that again?
We can't leave it as log cosine theta to the negative 1.
You could have left it like that too. Actually, in the book, they just left minus log of cosine, absolute value of cosine theta. I just took it one more step. Okay? So we could have left it just like this instead of plus c. They could absolute value. I mean, anytime you take the log, if it's something that could go negative, you have to put absolute value first. If it's something that's always positive, like x squared, then you don't have to put absolute value. Actually, I do like my form just a little bit more than theirs, because you can take care of this by putting absolute values here, but you see, you can still have cosine theta could still be 0, and you can't take the log of 0. You see, secant theta is never 0, so you eliminate that. So that's why this answer.
They took it to the secant on the
Oh, they do. Okay. Shame on them for tricking me like that. Oh, there it is. There it is. Yeah, you're right. I thought the answer was at the bottom of that page. Yeah, so that's what they get. And that is really the better way to express the answer. Okay. Now, did your little rule that you made up work on these two? The one that you said, oh, you just do an antiderivative.
No.
No, okay, you left that one alone? Okay. If you hadn't by then, you will on this next one. Okay? Believe me. All right. Let's try this one. The integral of x times the square root of 5x plus 1 dx. Now, I think I mentioned to you before, I don't really like having variables in a denominator. I like to move them to the numerator and make a minus exponent, right? Remember when I said that? Neither do I like to try to integrate something that has radical signs in it. I like to write that in exponential form as well. So let's do that first. That would be what? The integral of x times 5x plus 1 to the 1/2 power. You got it. Dx. Okay, I like that much better. And then what would you do next?
U equals.
Let u equal what? 5x plus 1, the innermost part of the most complicated part, right? So that would be 5x plus 1. Good. Then, next step, du is equal to 5 dx. Okay. Good deal. Well, we don't have a 5 dx, do we? We have a dx, but not a 5 dx. So one thing we might choose to do is divide this by 5. That will give us just a dx. But Houston, we still have a problem, don't we? Because you got that x in there.
No.
What's that?
I thought his name was Houston, so I thought it was
Okay.
Ronnie that.
No, okay, you've never seen Apollo 13, have you? There's a very famous line from that. You know what Apollo 13, do you know what I'm talking about? Okay. Apollo 13 was one of the missions to the moon.
I know what it is.
Okay, what happened?
They were crashing down, and then the parachute didn't work, so they let them in the ocean.
Yeah, and they had to fly the little lander back, basically. But when they found out they had a problem, they said, Houston, we have a problem. That was the famous line. I mean, it really happened. They said that. And then Ron Howard made a movie with Tom Hanks, and I can't remember the other guy in it that starred in it. They made a movie on Apollo 13, and they used that line. Houston, we have a problem. So that's what I would say. Or I named them Houston 1. I don't remember. I can't remember which I did. Okay. Or maybe I named you Houston. Okay. Did you ever think of that? Okay. All right. We need an X by itself. Impossible to get it? Couldn't we solve this equation for X? What would we got? How would we do it?
Got x equals negative 1/5.
Okay. You would subtract 1 from both sides, right? And that gives you a u minus 1 is equal to 5x, because this adds to 0. And then divide by 5, right? So we have x is equal to u minus 1 over 5. So let's put all our pieces together now. We have an integral. We have a 1/5 out front from the du, That dx is 1/5 dx, so that's going to make it a du there with the 1/5 out front. We have another 1/5 out front from the x is u minus 1 over 5, so let's make that a 25 out front. And the x becomes a u minus 1, and the 5x plus 1 is what? Five x plus 1 is a substitution. Didn't we say this is equal to that? B u to the 1/2, right? This tells us what x is. U minus 1 over 5. So, I may be skipping too many steps. If I do this, yell at me or something, okay? And then I'll kick you out of class, okay? I'm just kidding, okay? All right. All right. Let's write down what we've got, okay? Okay. We've got u is equal to 5x plus 1. We've got du over 5 is equal to dx. And we have u minus 1 over 5 is equal to x. Don't we have all three of these things? There's our substitution, there's our x, and there's our dx, right? So let's write them down. We've got the integral of x. Well, x is this thing, right? Okay, so that's going to be, I'm going to pull the 1/5 on the outside and have a u minus 1. That's our x, right? Okay, we have a 5x minus 1. What's that? U, okay. And that's going to be u to the 1/2. And then we have our dx, and our dx is du over 5. So there's the du. I'll put another 5 out front and make it 25. Okay. Was that any better? Made it a little clearer? What's wrong with me? Okay, never mind. I shouldn't be doing that. I should keep it confusing, shouldn't I? Make it seem like I'm smart. Okay. Now, is this any better? How so? See, that form, you can't multiply an x inside a radical. This form, this is a u to the 1/2. You can distribute that inside here. Can't you? Please say yes. Yes. All right. How does that go, then? 1/25, the integral of, what's u times u to the 1/2? Say again? You're distributing. Say again? U to the 3/2. U to the 3/2 minus u to the 1/2 du. Can we do that integration? Sure we can. This is 1 over 25. Don't forget that. What's the antiderivative of u to the 3/2? Okay, let's do the u part first. U will be raised to what? To what? No, you add 1. When you integrate something, don't you add 1 to the exponent? 5/2, okay. But then we also have to do what? Over 5/2, which is dividing by 5/2. But dividing by 5/2 is the same as multiplying by 2/5. Okay, that's that part. Minus you know what we got in this room? A right-hander. Both of us are lefties. Have you ever been in a minority before? How does it feel, huh? Okay. U to the 3/2 times 2/3. All right. Now what do we need to do? Plug in what U is. That's 1/25 times 2. And what is your U? 5x plus 1 to the 5/2 over 5 minus 2 times 5x plus 1 to the 3/2 over 3. One more thing. Plus C, don't forget your plus C. Okay. Now, I'm not sure they leave it in that form. Let's see what they do. Okay, no they don't. Well, the next to the last line, no it isn't. Okay. So what they do, and again, if you're doing web assigned, they want it exactly their way. That is a perfectly correct answer, but how they then write it is 2 over 2 over 125 times 5x plus 1 to the 5/2 minus 2 over 75 times 5x plus 1 to the 3/2 plus C. Why is that any better? I'm not sure. I would have been real tempted to pull out a 2 over 25 and then leave this a 1/5 of this and a 1/3 of that. But there's tons of ways you can write exactly the correct answer many different ways, and your computerized homework problem set up looking for one and only one answer, and it tells you you're wrong if you don't have it, which drives me nuts. But they did it right. That is a correct answer. Good deal. Now, what did you notice about all those examples we just did, besides them being a lot of fun? Okay? Well, they were fun. That's why I already said that. Okay? They were all what kind of intervals? They didn't have limits. They were indefinite intervals. So you had those plus C's that you kept forgetting, right? Okay. What if you have a definite integral? Okay? Now, you could do it just like you did before and treat it like an indefinite integral and carry it all the way through and then go back and get it all the way back into the original variable and then plug them in. It's a lot of extra work. And have I told y'all before what I feel like makes a good mathematician? There's several things, but one thing is you need to be just a tad lazy. Do either of you qualify? No. Okay, you're hard working. You can still do it. Don't sweat it. Okay? But I think to do math well, you have to be a little lazy because you're always looking for the easiest way to do a problem. Okay? I think that's what good mathematicians do. And here's what we do. Rather than forgetting about the limits and doing that and then getting back to x's again, why not, when you make your substitution, figure out what u of a is and u of b is, and then do this, and then when you do this, you just plug those values in, and you don't have to go back again. Because guess what? In a definite interval, Okay? You just evaluate. So, why don't you evaluate as you go? And then you never have to do those. That was the pain in the neck, wasn't it? To get it back to X's again. You don't have to if you get it to use in the first place. Okay? Let's try it. All right. I think that's the graph for the problem we're going to do. Here is the integral. Integrate from 0 to 2 x squared times the square root of x cubed plus 1 dx. There's our problem. Okay. I haven't written it very prettily, but that's the problem. Okay? Start it just like we did before. What would you do first? Okay, let u equal. I got that. X cubed plus 1. I like it. Okay? In fact, you might have even said, in fact, I'll do it in the next step. Then, du is equal to 3x. I'm sorry? 3x? 3x squared dx. Okay, right? Okay. Now, we don't quite have what we have up there, so what could we do? Divide by 3. Right, that gives her x squared dx. Okay. Now, here's the other little part in here. I'm going to change this to u's now. Okay, so it's going to be an integral, but I'm going to change my limits. Okay, so first I'm going to plug in. Remember, this is, I hope you remember this, whatever your d here is, that's x equals 0 to x equals 2. All right? So what I'm going to do is plug in x equals 0 here, and what do you get? U is equal to 1. So your lower limit here is going to be 1 when you get to u's here. Okay? And nine. Okay? When you plug in x equal 2, 2 cubed is 8, plus 1 is 9. Very good. All right? I wrote a du there, but I have to put my 1/3 out here for this to work. That dx becomes du over 3. There's your du. There's the over 3. Okay? The x squared was already incorporated there. But rather than writing a square root, I'm going to write it as, I don't even need a parentheses either, do I? U to the 1/2, right? Because it's that thing to the 1/2 power, but that thing is u. U to the 1/2. There it is, right? Can we antiderivative that? Please say yes. Okay. And that's going to be 1/3 u to the 3/2. Say again? Okay, certainly over 3, 2/3 times 2/3, right? It's over 3/2. That's the same as times 2/3. All right. Now, before I do my evaluation, I'm going to go on and pull out those constants. That's going to be 2/9 u to the 3/2 evaluated from 1 to 9. Okay. It's going to be 2/9 times, plug in a 9. Now, what does it mean to raise a number to a fractional power? 9 would be to the 3 halves. That means either 9 cubed and take the square root of it, or take the square root of 9 and then cube it, which you reckon is easy. Second, for sure. Keep the number smaller. So what you're doing, you're raising that number to that power, but taking that root off. So if you can, take the root first. Okay. Square root of 9 is 3, and 3 cubed is? Second? Yes, exactly. So that would be 27 minus, and then do the same thing for 1. That's really hard. Pull out the calculator for that. Was it? Oh, that's 1. Okay, we got it. What's that? Okay. When you're plugging in 9 for the u, that's what you're doing, right? So it's 9 to the 3 halves power. You can do it either one of two ways. You take the 9 and cube it, and then whatever that answer is, take the square root of it. Or take the square root first, square root of 9, and then that answer you cube it. That's the easier way to go. Okay, that's what it means to do a fractional power. The numerator is the power, the denominator is the index for your root. That would be a square root. And that would then be 2 ninths times 26. And I don't think 9 will go into that, so that'll be 52 ninths. That's what I got. How did they do? Oh, man. Oh, look at that. They got it right. Good for them. Okay. Make sense? You think we can squeeze one more in? Yeah? Okay, let's do it. All right. This is so much fun. All right. Example 9. Integrate from 0 to pi fourths tangent cubed theta secant squared theta d theta. Aren't you glad that you said let's do another one? All right. How are we going to do this? How are we going to do that?
You gotta change everything to sine and cosine.
A little louder?
Change everything to sine and cosine first.
You might be able to, but I think this is easier to do it straightforwardly here. What is something to keep in mind? Does anyone remember the derivative of either one of those? What's the derivative of tangent? You got it. The derivative of tangent is secant squared. So therefore, I think I'm going to want to say let u equal what? No. I'm sorry. It was just so much fun. Okay. Tangent. Let u equal tangent theta. Okay. Then du is equal to secant squared theta d theta. Okay. Very good. Now look at that. What does this become? Okay. Except we got to do something with our limits. If theta is equal to 0, what's u? It's tangent of 0. Oh, pull out the old blue box, huh? 0. Okay. And what's tangent of, if theta is equal to pi fourths, what's tangent of pi fourths? 1. The box slows you down a little bit, but okay. All right. What do we have left then? What's that? Oh, no. Okay. You're going to get lost. Never mind. No. Okay. What do we have here then? U cubed du. Look at that. This part is your du, and this part is u cubed. Can we do that? Please say yes. Okay, what does that do? U to the fourth over, what do you say, 4, okay. Evaluate that from 0 to 1. What do you get? I'll do the second part. Okay. 1. 1/4. Okay. Okay. See it? Did you ever think that was going to come out that simple? And that's exactly what we got in the book. Now the sad news. We're out of time. Sorry about that. Get over it. Okay? We will start next time with example 10. We almost finished this section. Okay? Homework exercises will be do any of the odds 1 through 5. Those are really easy. Okay? Then do any of the odds 7 through 23. Okay? Then do either 25 or 27. You choose, either or both. And then do any of the odds 29 to 74. I'm sorry, 73 odds. Okay? Try to do 75. Well, let me see. Try to do any of the odds 75 through 79, and then do any of the odds 81 through 95, and try to do any of the odds 97, or either 97 or 99 or both, and either 101 or 103 or both, and try to do 105. If you can't do it, don't sweat it. If you're interested in the further insights and challenges, you can go for that. But let me back up one. Here on number 99, they talk about Rayleigh distributions. Okay? It's talking about wind engineers, which I'm guessing that's going to be pretty close to civil, won't it be? Don't you think civil engineering will get a little bit into that? That may be something if one of you wants to write a paper on who in the world was Rayleigh, or how did he come up with these Rayleigh distributions, or what's other applications of them, or something like that, by all means you can give a look at that. Or not. You may find that not very interesting either. But I always look for something like that to see if possibly you might find a paper topic there. All right. Now, once we do example 10, I'm going to do a little bit in 5/8, okay? Because that's some pretty important stuff. I may not do it all, but I'll do a little bit of that. And then we'll get into chapter 6, okay? And your first test will be, all right, okay. 5.9 is really interesting stuff. We just don't have time for it, so we're going to skip that. But I encourage you to look at it, because you may see that in future courses too. I don't know that you will, but it's a possibility. And then after that, we'll move into chapter 6, applications of the integral. So your first test will be covering 5, 7, and basically most of chapter 6. So we got a ways to go before we get there, but hopefully we'll move on now. Sorry it took us that long to start, but I felt like you did need that stuff. Good deal. Any questions? All right, have a good weekend. Working on calculus problems makes it a good weekend, right? Working on research papers makes it a good weekend, right? All right.
It was a nice day to get 4 bonus points, right?
What's that? If you get it in this month. You only have today and tomorrow to get it in this month. Yeah, you get 4 bonus points. Next month will be 3. Good deal. We'll see you Monday.